Welcome to qnawire.
For this question, we want to figure out the symmetry group of a square. And we're given this sort of setup with the different axes of a square and these labelings 1, 2, 3, and 4 for those axes. And I'll also add here some colors on the corners just to identify them. And I would recommend for this problem, when sorting out this group and the table, to actually make a physical square out of a piece of paper. So just cut out a square on a piece of paper, and either with different colored pens or just write numbers on each corner on both sides. So each one should have the same identification on each side, and maybe even what you want to set as like your, say, identity element, or just like your regular square. Maybe make draw an arrow or some indication that that's like the front of your square that you're considering. So with that, we can think about what these symmetry operations are. Here we're going to have rotations and also flips across different axes. So I'm going to say for my group, the way I'm going to identify this, we'll have an identity element, which we could relate to a rotation by 2 pi. So we can consider that. So just think we're rotating, or you could take your physical piece of paper, we're rotating this green dot all the way around. We could think about it like that. We're also going to have, and I'll label rotation R, is a rotation by pi over 2. So that's moving this green dot over here. So just rotating the square. And I'll label that R, and I'll do R prime is then also a rotation by 3 pi over 2. And that would be taking this green dot all the way this way, which we could also think about it also as a rotation by pi over 2 the other way. And then also we'll have flips. So here we have 4 axes, and we're going to have an axis across, we're going to have a flip across either of those, all of those rotations, all of those axes, sorry. So I'm just going to label those for our purposes. I'm going to label it F sub I. So that's a flip about the mi pi axis. So if we want to identify which of these is what order, oh yes, so this is I is between is 1 through 4. We have one more rotation here. Actually, we have a rotation by pi, which is like we move this green dot all the way over here. So let's call that Q. So that's a rotation by pi. So these are our 8 symmetry operations. We have 1, 2, 3, 4, 8. And here we can think about these are going to be order 4. This is order 1. These are order 2. And this one is order 2. So now we can think about populating this table. This is pretty tedious, but if you have the physical piece of paper, it becomes pretty easy to write out and fill in the blanks. Of course, we just write all of our elements of our group as we've labeled them on each axis of the table, and then we fill in the results of the operation. So where the operation is doing one of those operations and then the other. So we can see some things from this table. We again see how these are order 2 elements because if we do the operation twice, we get the identity. We can see that here. And we can see some subgroups that form. Here we can see subgroups, and we can see that by the fact that there are no other elements in the group in this subset of the table. And likewise, here we also get a subgroup. So here that's just highlighted, these two subgroups we get. We can also think that we have order 2 subgroups as well for each of the order 2 elements because those are going to be cyclic, and all of these are proper subgroups of this group, the symmetry group. So again, this table, once you have it, it'll give you a lot of information. We could also see from it that this is a non-abelian group, similar to the triangle symmetry group. But yes, once you fill out the table, it takes the longest, but use the physical square and it makes it a lot easier. We could then think about what the cosets are. Remember, a coset is you take that subgroup, say we take this subgroup and we consider each element of the group that's not in it, and we multiply or whatever operation here, and you put it either on the left or the right. For both of these order 4 subgroups, the left and the right cosets are the same, and for each element you end up getting the same thing. So of the subgroup of rotations, you end up getting the flips across the different axes, and for this subgroup, this is what you get out. And that's, again, you can read that off from the table as well. Think about for each other, so here, these are the only other elements that aren't in this subgroup. For each one, if you left or right multiply on here, if we look at the table, this is what we're going to get, this result for each one. Yes, so we could look at the 2-element subgroups as well. And for the one that's rotation by pi, our left and right cosets are going to be the same for that, and this is what they look like. Again, we could get this from the table. Just going through all the 6 other elements, we're going to get just these 3 unique ones. And for these other ones, we'll get some similarities, but our left will have some left and right coset. So here with the left coset, if we consider the right coset instead, these would just be flipped, like which ones are paired with which. So it would be like R prime and F4 instead. But just, if you say left coset, this is what you get. You could write out the right cosets as well. But these are the same regardless of if you consider left or right. You'll have these like Q, F2, etc. But yeah, so big thing here, writing out the table. Make a physical square on a piece of paper, and it'll make the whole process a lot easier just to do these identifications and see what the results of the different operations are.